and thanks for tuning in with this video. In this video, I'm gonna go over the demo of my final project, line by line of code. So to start off, I'm gonna capture the live frame from my Intel depth camera. And in this script, what I'm going to do is I'm getting the live frames. I'm going to import it into my car detection script. So here, capture the live frame from the camera. So this is where you configure the pipeline for your depth camera. Right now, it's the pixel size is between 640 to 480, and it's in BGR, and this is a 15 frames per second. This line of code, it enables the stream, and you start the pipeline, and here you wait for the frames, and in this code you will write the new image to this directory for later use. And this is a code to load the image. So I'm gonna quickly go over the proof that it gets the live frame as you run the code by putting my hand in between. So here you could see a proof that it works, and we run that again. And here in the car detection code, I'm going to get the CV2 library and NumPy, matplotlib for the graphing the simulation of the robot where it's at in the coordinate system. And this is the Opentrons API to control the robot arm. Same, you will load the image that we captured from the frame capture code, and then you would just convert the image to BGR to RGB to show it in the cell right here. And now you're gonna define the range for masking for red, blue, and green color. In this image, I found that the lower red and the upper red, these masks that I'm going to apply later on, are between 0 to 19 and 160 to 180. And this is the hue, saturation, and value in HSV space, color space. The same goes for blue color and green color. These are the ranges, as you guys can see here in this code. And this is a list of arrays. And here you convert the RGB to HSV color space because it's easier, because in RGB you can have a lot of noise, and in HSV color space you don't have much noise or disturbance. Here in this function I have in red dot, here I'm applying two masks. If CV2 is in the range of the HSV image and this masks, right, and it will find these ranges that I've given in the previous line of code, and then you will go bitwise mask 1 and mask 2, meaning that you will mask it, and then you combine the mask and you apply the mask to the image. And then you for further noise clearance, you would get the red dot, the image, and you will use this kernel size to clear up a lot of noise in the image. And here you're converting after masking, you need to convert the image from HSV from BGR to gray to use. First you will get the mask image in here in the CVD color function, and then you will convert it to BGR to grayscale image. For Hughes circle transform, Hughes circles, what it does is it gets the circles in the image. So you will get the input gray image, and then you will give the parameters and the radius, minimum and the maximum radius, and the parameter of the circle 1 and 2, and then you will draw the circles whatever you found with this function on the image. And these are the font of the detected color, so we'll say where it's at on the pixel space. And then if circles is not found, then you will just give the output frame. If it's found, then you will give the detected colors. And in this code, you will label the circle with its center coordinate, like you will give like 154 so 60, which is xy, the coordinates in pixel space, and you display the image. And it's the same idea for the blue function, but the difference is I only gave it a lower and the upper, just one range, and I just apply the mask. Instead of combining two different masks, I'll just give it one mask. The same idea, you give it the Gaussian blur, and then you will just draw the colors or draw the circles that I found. And the same idea for the green dot. In this case, I gave it two different masks, and you do the bitwise operation to combine them, and you apply the mask. And here in this function, every time you will return the green circles, the output frame, and the pixel value of the circles that we detected. And this return this return will be used in our user input, so we can analyze where you want the arm to go. So in every function I'm returning, for example in red, I'm returning the circles red, which is this, which is circles, which is the found circles, and the output frame, which is the image, and then the pixel value, which is the value on like a circle, and then it will have the value. Then you connect the robot using the Opentrons API, and then here you can see connect your robot here, and you home the robot to reset it. Then you again you reset the system at the starting point, and here you could see this is like a simulation to show like currently the robot is homed. As you can see, the x, y, and z values are all zeros except the x, because of x is here, so you can see the robot is currently homed. It's not anywhere else. So x, y, and z. So this is a simulation. And then in this function, move red, move blue, and move green, I'm extracting. In the previous function, I was returning the pixel value for red, pixel value for blue, for green. You extract the xy, and you convert by giving it the offset in the robot deck, and you subtract the value by measuring the deck itself, and then you feed your offsets to move that robot. Remember, first you extract the xy values of the coordinates in the image, then you give the offset with the robot deck for red, blue, and green. Now here in the end you will see all the outputs. Now this is a simple user input if else statement. Now you're saying if the color choice is red or blue or green, and here you're returning the detected red circles, the image, and the pixel value, which we will see here. And then you're saying, okay, if the red is there, display the red color in the image, output frame, and the pixel value, and then move the robot to that red. And then you get the head position, and you move the robot down to touch the red dot by 95 millimeters. Same for blue, same for green. You extract the blue image, and then you also display the frame, and you get the pixel value. Same for green. You get the green circles in the image. You get the output frame, and you get the pixel value from this function. You're extracting this return from this function to this here, to these three variables. Move the green, go down z. If it's not red, blue, or green, you will just simply say it's an invalid choice. Now, here, as a test, I'm gonna write red. And please note on the right side, you will see the robot arm coming to the red dot. So here, as you can see, this is the circle's red, the output, the masked output. This is that pixel red frame. You get the value and you get the red dot. Here, it's the arm is going to touch the red dot. And this is the robot. It's add from this and moved to this color space, to this area, to this spot. Now again, we run the whole code, we home the robot, we reset it. Then we're gonna do the same for blue and green. Now it's prompted, so set blue, and same idea, you will see the mask, blue mask, you have chosen the blue color, it goes to the blue mask, where is blue in the pixel system. This is the data, X, Y, and Z, and this is where the head moved. Same, you reset the robot again, and then you will also then it's gonna be prompted for green. Thanks for watching. In my next video, I'm going to explain the depth detection as a safety feature. Please stay tuned for the next video. Thank you.